Pick up something small and heavy, a coin, a key, a smooth stone, and let its weight settle into your palm. Almost none of that weight is what you think it is. The solid matter inside it, the actual particles, accounts for only a sliver of the heft you feel. Nearly all of it is energy, the energy of a force locked inside every proton, churning far too fast and far too small to ever see. That force is the strong force, and the place it hides is the proton at the very heart of every atom in your hand. Over the next 2 hours, we'll build up to it slowly, one simple step at a time, starting from a question you can hold on to. What keeps a proton together, and why does it weigh what it weighs? If you enjoy this kind of slow, patient look at the universe, take a moment to subscribe, and we'll begin. Hold that weight a moment longer. Whatever you chose, a coin or a key or a stone, it is built from atoms, and nearly all the mass of every atom lives in its core. The core is made of protons and neutrons, and they are heavy compared to everything around them. The cloud of electrons that fills out the rest of the atom weighs almost nothing by comparison. So when you feel the heft in your palm, you are mostly feeling protons and neutrons, packed by the trillions into the matter you're holding. Now we can ask a sharper question. What gives a single proton its weight? For most of the last century, the obvious answer was the stuff inside it. A proton is built from smaller particles called quarks, 3 of them, and surely the proton weighs what its parts weigh, the way a bag of marbles weighs as much as the marbles inside. It is a reasonable guess. It is also wrong, and the size of the error is the whole story. We have measured the masses of those 3 quarks. 2 of them are up quarks and 1 is a down quark, and they are very light. Add all 3 together and you get only about 1 part in 100 of the proton's mass. 1%. The other 99% is not matter at all. It is energy, bound up inside the proton and given weight by the most famous equation in physics, the one that says energy and mass are 2 faces of the same thing. That equation, energy equals mass times the speed of the light squared, is usually told backward as a recipe for turning a little mass into a great deal of energy. A bomb, a reactor, the sun. But it runs the other way just as well. Trap enough energy in a small enough space, hold it there, and that trapped energy weighs something. It has mass. And almost all the mass of the proton, almost all the mass of you and the chair you're sitting in, and the planet under your feet, is energy held in place by a force. The force has a plain name. It is called the strong force, and it is the strongest of the 4 forces we know. It is also the most hidden. You never feel it directly, because it does not reach past the edge of an atomic nucleus. Its whole life is lived inside the proton and the neutron, in a space so small that 100,000 of them laid in a line would still not cross a single atom. Down there, the strong force is doing something furious and constant, and the weight in your hand is the bill it sends up to our world. So here is the question this whole story will answer, asked as plainly as it can be. What holds a proton together, and why does it weigh what it weighs? Those turn out to be the same question, and the answer took the better part of a century to find. It required taking the atom apart, then taking the nucleus apart, then taking the proton apart, and at each step the picture got stranger, and the math got harder, and the people involved got more confused before they got less. We will walk it slowly, the way it really happened, one step at a time. We will start where everyone started, with the atom and its tiny crowded heart, and we will not rush. By the end you will understand in plain terms why the thing in your hand weighs what it does, and why that answer is one of the deepest things we have ever learned about the world. For now, just hold the weight and keep the question close. We begin at the center of the atom. To find the proton, you have to go inward, past every familiar scale, until the ordinary world falls away. Start with the thing in your hand and imagine cutting it in half, then in half again, and again, far past what any blade could do. Eventually you reach a single atom, and the atom is already almost nothing. It is mostly empty space. If you could blow one up to the size of a cathedral, the dense part at its center would be no bigger than a grain of salt hanging in the middle of the great open hall. That grain of salt is the nucleus, and it is where the protons live. An atom of the lightest element, hydrogen, has just one proton at its centre and one electron drifting far outside it. Heavier atoms hold more. The carbon in your bones carries 6 protons in its core, the iron in your blood carries 26, the gold in a ring carries 79. In every case, the protons sit at the very centre, and the electrons keep their distance, held in place by the pull between opposite charges. The numbers of scale here are hard to feel, so let me give them to you slowly. A single atom is about 1/10 billionth of a metre across. The nucleus inside it is roughly 100,000 times smaller still. That ratio is the strange part. The nucleus holds almost all the weight of the atom, yet it takes up almost none of the room. Everything you think of as solid, the table, the floor, the bones in your hand, is overwhelmingly empty, with tiny heavy cores scattered through it and a haze of electrons in between. Put it another way, if you shrank an atom until its nucleus was the size of a marble, the outer edge of the atom would stretch about a kilometre away, and the whole vast space between would hold nothing solid at all, only the faint presence of the electrons. When you press your hand flat against the table, and it does not pass through, you are not feeling solid matter meeting solid matter. You are feeling the electrons in your hand pushing against the electrons in the table, 2 clouds of like charge refusing to overlap. The hard, certain surface of the world is mostly that refusal. The real matter, the part with the weight, is hidden far below it in those scattered grains of salt. So the proton sits at the bottom of everything, at the centre of the centre. To study it, physicists had to first prove that this tiny dense core existed at all, because for a long time no one knew the atom had a heart. The early picture was softer and vaguer, a blur of charge with no firm middle. The story of the proton really begins with the moment that blur was shattered, when a thin sheet of gold revealed that the atom is mostly nothing wrapped around a hard secret point. Picture again that grain of salt in the cathedral. Now picture that even the grain is not solid. Inside it the protons and neutrons are packed together, touching, jostling, held by a force we have not met yet. And inside each of those protons, smaller still, is the thing this whole story is chasing. We're going down through layer after layer, and at every layer the rule is the same. The mass stays concentrated, the space stays mostly empty, and the forces holding it together grow stronger and stranger the deeper we go. For now, hold this one idea. The world feels full, but it is built around tiny crowded cores with vast emptiness between them, and the proton lives at the heart of those cores. To see how we learn this, we go back to a laboratory in England, more than 100 years ago, where a few researchers fired particles at a sheet of gold and watched, baffled, as some of them came straight back. At the start of the 20th century, the accepted picture of the atom was soft. The leading model imagined the atom as a ball of spread-out positive charge with electrons dotted through it, the way fruit sits in a pudding. There was no hard centre, no concentrated core. Positive charge filled the whole atom evenly, and the light electrons were sprinkled inside it. It was a reasonable idea, and there was no obvious reason to doubt it. Ernest Rutherford, working in Manchester, decided to test it. Rutherford was a New Zealand farmer's son with a booming voice and an instinct for the decisive experiment, and he had already won a Nobel Prize for his work on radioactivity. He had a tool that earlier scientists lacked, a steady source of alpha particles, which are small, fast, positively charged fragments thrown out by radioactive atoms. He set 2 younger researchers, Hans Geiger and Ernest Marsden, to fire these alpha particles at a sheet of gold foil hammered so thin it was nearly transparent. The expectation was simple. If the atom were a soft pudding of charge, the alpha particles should sail straight through, barely bent, the way a stone passes through fog, and most of them did exactly that. But Geiger and Marsden noticed something that should not have happened. Once in a great while, an alpha particle came back. Not bent a little, but knocked almost straight backward, as if it had struck something hard and immovable. Rutherford was stunned. He later said it was about as astonishing as firing a large artillery shell at a sheet of tissue paper and having it bounce back and hit you. A soft, spread-out atom could never do that. Nothing inside the pudding picture was solid enough or concentrated enough to turn a fast alpha particle around. For one of those particles to rebound, it had to hit something small, dense, and carrying a strong charge, packed into a tiny fraction of the atom's volume. By 1911, Rutherford had worked out what the bouncing meant. The atom was almost entirely empty. Nearly all of its mass and all of its positive charge was squeezed into a minute core at the centre, which he called the nucleus. The electrons, light and negative, were out beyond it, filling the great empty space. Most alpha particles passed clean through that emptiness untouched. The rare one that scored a near-direct hit on the tiny nucleus was thrown violently back. This is the moment the modern atom was born. Not a pudding, but a near vacuum built around a dense, charged point. The numbers Rutherford pulled from the scattering told him the nucleus was thousands of times smaller than the atom around it, yet it held essentially all the weight. It was the grain of salt in the cathedral, and now there was hard evidence it was really there. The discovery raised a new puzzle almost at once. If all the positive charge was crammed into that tiny nucleus, then in any atom heavier than hydrogen, there were several positive charges sitting right on top of one another, closer than anything in ordinary experience, and like charges push apart. The closer you force them, the harder they shove. Inside the nucleus, the push between those packed positive charges should have been overwhelming, enough to blow the core to pieces in an instant. Yet the nucleus did not fly apart. The gold foil sat on the bench, stable and ordinary, its countless nuclei holding together as if nothing were wrong. Rutherford had found the heart of the atom and proved it was small and dense, but in doing so he had set a trap for everyone who came after. Something had to be holding that crowded core together, fighting a force that should have torn it open. No known force could do it. Finding that hidden glue would take another generation, and it would lead step by step straight to the strong force and the secret inside the proton. Let me make the trouble inside the nucleus vivid, because it is worse than it first sounds. Take two protons, each carrying a positive charge, and bring them close. They push apart. This is the same force that makes your hair stand up on a dry day and snaps a spark from a doorknob. The electric force between charges, and its rule is steep. Halve the distance between two charges and the push between them grows 4 times stronger. Bring them 10 times closer and it grows 100-fold. Now squeeze those protons down to the size of a nucleus, where they sit almost touching, separated by less than 100,000th of the width of an atom. At that range, the electric push between two protons is enormous. Scaled up to something you could feel, it would be like trying to hold two powerful magnets together at their like poles, except far worse, a shove that grows more violent the closer you press. Pack a dozen protons into a heavy nucleus, and every one of them is shoving against every other, all at once, all trying to escape. By every rule known in 1911, the nucleus should not exist. It should detonate the moment it forms, flinging its protons in all directions. And yet there it sat, in the gold foil, in every atom of the bench and the building and the people standing in the room. Carbon held 6 protons together without complaint. Iron held 26. Uranium held 92, all crammed into a space far smaller than any instrument could then resolve. The most crowded, most repulsive arrangement imaginable was also, somehow, one of the most stable things in nature. Nothing in the known physics of the day could account for that. So there had to be another force, not gravity, which is far too weak between objects this light to matter at all, not the electric force, which was the very thing causing the problem. Something new, something nobody had named, had to reach in among the protons and pull them together hard enough to overpower their mutual shoving. It had to be strong, stronger than the electric repulsion it was beating. That is the first hint of the name it would eventually carry. But strength alone was not enough to explain what was seen. The new force had to have a second, stranger property. It could not reach very far, If a powerful pulling force stretched across long distances the way gravity and electricity do, it would clump all the matter in the world into one dense lump, and we would not have ordinary chemistry, ordinary atoms, ordinary space between things. The fact that atoms sit politely apart, that the force does not yank distant nuclei together, means whatever holds the nucleus must switch off almost completely just outside it. This is the shape of the puzzle, a force that is ferociously strong when protons are nearly touching, and then vanishes as if it did not exist once they're even slightly farther apart. Strong and short, powerful and blind beyond its tiny reach. Nothing in the physics of the time behaved that way. The known forces faded smoothly with distance and never simply stopped. This new thing had a hard edge. For years it was just a gap, a hole in the picture where an explanation should be. Physicists knew the force had to exist because the nucleus existed, but they could not say what it was or where it came from or what carried it. The bench held the answer in plain sight, in every stable atom, and no one could read it. The first person to guess the right shape of the missing force was a young theorist in Japan, working mostly alone, who proposed that the glue inside the nucleus was passed back and forth by a particle no one had ever seen. In 1935, a Japanese physicist named Hideki Yukawa took the puzzle of the nuclear glue and made a bold, specific guess. He was in his late 20s, working at a time when Japanese physics was still building its place in the world, and he had been turning the problem over for months. He started from an idea that was just then reshaping how physicists thought about forces, the idea that a force between two particles is carried by a third particle passed between them. This was already the picture for electricity. When two electrons push apart, physicists had begun to describe it as the two particles tossing a particle of light, a photon, back and forth between them. The photon is the carrier of the electric force. It has no mass, and that masslessness is exactly why the electric force reaches across the whole universe, fading slowly but never stopping. A massless carrier travels freely and far. Yukawa's leap was to ask what would happen if the carrier of the nuclear force were not massless. He worked out a clean relationship, one that tied the reach of a force to the weight of whatever carried it. A heavy carrier cannot travel far before it must be reabsorbed, so a force built on a heavy carrier would have a short reach. The heavier the carrier, the shorter the range. This was the missing piece. A force that switches off just outside the nucleus needs a carrier with real mass. From the known size of the nucleus, Yukawa could estimate how heavy that carrier had to be. The answer landed in between. His particle would be far heavier than the feathery electron, but lighter than the proton itself, somewhere around 200 times the electron's mass. Nothing like it had ever been seen. It sat in an unexplored middle zone, and because its mass fell between the electron and the proton, it would later be called a meson, from a Greek root meaning middle. The name would eventually spread to a whole class of particles built in the same way, but it began here with a single predicted carrier sitting in the gap between the two particles everyone already knew. The logic was tight, and the prediction was concrete. Yukawa was not just saying a force existed, he was saying a new particle existed, with a mass he could roughly name, and that this particle was constantly being swapped between protons and neutrons inside every nucleus, binding them together. Pull the protons apart and the exchange weakens fast, which is why the force has its hard, short edge. Inside the nucleus, the swapping is furious, and the binding is fierce. At first, almost no one outside Japan noticed. The work was published in a journal that few Western physicists read closely, and the idea of inventing a brand new particle to fix a problem struck many as too easy, even reckless. You could explain almost anything by conjuring a new particle. The real test was whether nature really contained the thing. A prediction like Yukawa's is only worth something if someone goes looking and finds exactly what was promised, with the right mass and the right behaviour. So Yukawa's meson hung in the air as a beautiful possibility, unconfirmed for over a decade. The world had other concerns in those years, and the search was slow and difficult because no machine of the time could make such a particle on demand. The only place energetic enough to produce it was the sky, where cosmic rays from deep space slam into the upper atmosphere with far more energy than any earthbound device could muster. If Yukawa's particle was real, it might be raining down through the air, faint and rare, waiting for someone patient enough to catch it. That search, and a confusing false alarm along the way, is where the story goes next. The hunt for Yukawa's particle ran into trouble almost immediately, and the trouble was a case of mistaken identity. In the late 1930s, two American physicists, Carl Anderson and Seth Neddermeyer, found a new particle in cosmic rays with about the right mass, a couple of 100 times heavier than the electron. For a while it looked like the meson had been found, and there was real excitement. But something was wrong. Yukawa's particle was supposed to feel the strong nuclear force intensely. It was, after all, the carrier of that force, so it should be grabbed and absorbed the instant it came near an atomic nucleus. The new particle did the opposite. It drifted through matter, passing close by nuclei without being caught, ignoring the strong force almost entirely. It had the right weight, but the wrong personality. This particle, now called the muon, turned out to be something else, a heavier cousin of the electron with nothing to do with nuclear glue. The real breakthrough came in 1947 from a team led by Cecil Powell in Bristol, England. Powell had spent years perfecting a quiet, painstaking method. He used special photographic plates coated with thick emulsion that recorded the track of any charged particle passing through them as a line of developed silver grains. He carried these plates up mountains and floated them on balloons high into the atmosphere, where cosmic rays are strongest, then brought them down and studied them under a microscope, track by track for months. Working with Powell were Cesar Lattes, a young Brazilian physicist, and Giuseppe Occhialini, an Italian, and together they found what everyone had been missing. In the emulsion they saw a particle that came to rest, and then gave birth to a second particle, the muon, which carried on. The first particle was heavier than the muon, and it behaved exactly as Yukawa had said it should. It interacted strongly with nuclei. It was made in violent collisions and then decayed. They named it the p-meson, soon shortened to the pion. Here, at last, was Yukawa's particle, 12 years after he had predicted it. The pion had a mass in the range he had estimated. It felt the strong force. It was the thing being swapped between protons and neutrons to hold the nucleus together. The muon that had caused all the confusion was simply a different particle that happened to share a similar weight, a coincidence that had thrown the search off for years. The discovery vindicated Yukawa completely, and the recognition followed quickly. Yukawa received the Nobel Prize in 1949, the first Japanese person ever to win one, a moment of real pride for a country still rebuilding after the war. Powell received his own Nobel Prize the next year for the method and the find. Two predictions, the existence of the particle and its rough mass, had both come true, and the nuclear force finally had a named carrier you could point to in a photograph. For a brief while the picture looked clean and finished. The atom had electrons on the outside and a nucleus at the centre. The nucleus was made of protons and neutrons. The protons and neutrons were held together by exchanging pions, just as the electric force was carried by photons. A few particles, a couple of forces, a tidy story you could draw on a single page. It felt like the puzzle was nearly solved. It was not. The same cosmic rays and the powerful new accelerators just coming online were about to pour out a flood of unexpected particles, far more than anyone wanted or could explain. The pion turned out to be only the first of a crowd. Instead of a clean ending, the discovery of the pion opened a door onto a chaos that would take 15 years to make sense of, and the simple picture of matter was about to come apart at the seams. Through the 1950s, the clean picture of matter fell into disorder. The cause was new power. Physicists had begun building accelerators, machines that drove particles to high speeds and smashed them into targets, and these collisions threw off particles never seen before. The cosmic rays kept adding to the haul. One after another, new kinds of matter appeared in the detectors, each with its own mass and lifetime and habits. There were particles a little heavier than the proton, and particles in between the pion and the proton, and particles that decayed in strange delayed ways that did not fit the expected timing. They were given names from the Greek alphabet as fast as they were found: the kaon, the lambda, the sigma, the psi, the delta, and more behind them. By the end of the decade, the count had climbed past 100. What had looked like a handful of basic building blocks was now a swarming, unruly collection with no obvious order. This was a genuine crisis, though a strange and almost embarrassing one. The whole point of digging down to the smallest pieces of matter was to find simplicity, a short list of fundamental objects from which everything else was built. Instead, the deeper physicists looked, the more pieces they found, and none of them seemed more basic than any other. 100 particles is not an explanation. It is a problem wearing the costume of an answer. The mood of the time is captured in a remark often attributed to Enrico Fermi, one of the great physicists of the century. He's supposed to have said that if he could remember the names of all these particles, he would have become a botanist. The joke stung because it was fair. Physics was meant to be the science of deep, simple laws, and here it was reduced to collecting and labelling specimens like so many beetles, with no theory to say why these creatures and not others. The particles did not seem random, though. As more were catalogued, patterns began to flicker at the edge of the data. Certain particles had nearly the same mass, and differed only in charge, as if they were siblings. Some shared a peculiar property, a kind of stubbornness that made them live longer than they should have before decaying, which physicists labelled strangeness, for lack of a better word. The strangeness came in whole units, and seemed to be preserved in the fast-strong interactions but not in the slower ones. These regularities were tantalising. They suggested that underneath the mess there was structure, some hidden bookkeeping that the particles obeyed. But seeing a pattern and explaining it are different things. You could line the particles up by their properties and notice that they fell into neat groups, yet still have no idea why those groups existed, or what deeper objects might be generating them. The zoo had an order to it, but the source of that order was invisible. What physics needed was someone who could look at the whole crowded chart and see the symmetry running through it, the way a musician hears the key that ties scattered notes into a chord. The particles had to be expressions of something simpler underneath, a smaller set of rules or pieces arranged in different ways. Finding that hidden arrangement would mean trusting the patterns enough to follow them, even where they pointed to things not yet seen. That trust was the breakthrough. In the early 1960s, working from the regularities in the data, a small number of theorists found a mathematical scheme that sorted the chaos of particles into clean geometric families. It did not just organise what was known, it left a gap, an empty seat in one of its patterns, and predicted that a specific particle, with a specific mass and specific properties, had to exist to fill it. The man who saw the deepest pattern was an American physicist named Murray Gell-Mann, and his scheme would crack the whole problem open. Murray Gell-Mann was a prodigy with a restless encyclopedic mind. He had entered college at 15, spoke many languages, and collected facts about birds and linguistics and ancient scripts with the same hunger he brought to physics. Faced with the chaos of the particle zoo, he did what he did best. He looked for the hidden symmetry, the rule that would let 100 messy particles fall into a small number of orderly families. In 1961, Gell-Mann found it, and an Israeli physicist named Yuval Ne'eman arrived at essentially the same thing independently at nearly the same moment. The idea drew on a branch of mathematics that describes symmetry, the study of the ways an object can be rotated or rearranged while staying the same. Gell-Mann realised that if you placed each particle on a chart according to two of its properties, its electric charge and its strangeness, the particles arranged themselves into tidy geometric shapes, mostly groups of 8. He gave the scheme a playful name, the Eightfold Way, borrowing a phrase from Buddhist teaching about the 8 steps to enlightenment. It was a joke and a description at once, since the most common pattern really did hold 8 particles. Plotted by charge and strangeness, the 8 would settle into a neat hexagon with 2 particles in the centre, a shape as regular as a snowflake. The proton and the neutron sat together in one such family, no longer alone but as 2 members of a larger group. What made this more than a filing system was that the symmetry was mathematical and rigid. The patterns were not loose groupings chosen by eye. They were the exact shapes that a particular symmetry, known to mathematicians as a structure built on the number 3, was forced to produce. The particles were behaving as if they were different faces of a single underlying object, the way one symmetry can wear many masks. The chaos of the zoo was the surface, the 8-fold way was the order beneath. The scheme sorted the known particles beautifully, but a filing system that only organizes what you already have is not yet science at its strongest. The real power of a pattern is prediction. A true symmetry does not just describe the seats that are filled, it tells you about the seats that are empty, and it insists they cannot stay empty. If the mathematics demanded a family of 10 and only 9 were known, then a 10th particle had to exist, and the pattern could tell you a great deal about it before anyone had seen it. This is where Gell-Mann's scheme stopped being a clever sorting and became a genuine theory of nature. Among the patterns was one larger family, a triangular arrangement that should hold 10 particles. By the early 1960s, physicists had found 9 of the 10. One corner of the triangle was empty. The symmetry said something had to sit there, and because the other particles in the family stepped up in mass in regular increments, the missing one's mass could be estimated with surprising precision. The pattern also fixed the missing particle's charge and its strangeness, the most extreme strangeness of any particle in the family. It would be a specific, predictable thing, not a vague possibility. Either it existed, with close to the properties the 8-fold way demanded, or the whole beautiful scheme was wrong and the apparent order was a coincidence. This is the kind of clean test that physics lives for, a prediction sharp enough that nature can give a plain yes or no. The particle the pattern called for was named the omega minus, and the search for it became a direct test of whether the symmetry was real. If it turned up where Gell-Mann's chart said it should, with the mass and charge the pattern required, then the families were no accident, and the particles really were built from something deeper. The hunt was on for a specific dot in a specific empty corner, and the answer would either crown the idea or sink it. The prediction of the omega minus was made in 1962, at a large physics conference where Gell-Mann, looking at the gap in the pattern, stood up and described the missing particle in detail. He named its mass, its charge, and its extreme strangeness, and he pointed physicists toward the kind of experiment that might make it. It was a public bet on the symmetry, laid down in front of the field, with the prediction precise enough to be proven wrong. Making the omega minus was not easy. It required slamming particles together with enough energy to create something heavier than the proton, and loaded with the maximum strangeness the pattern demanded. The place equipped to try was Brookhaven National Laboratory on Long Island in New York, which had a powerful accelerator and a large detector called a bubble chamber, a tank of liquid that revealed the paths of particles as strings of tiny bubbles. Physicists fired beams into the chamber and photographed the tangles of tracks, searching for the one rare event that would betray the new particle. In 1964, after sifting through tens of thousands of photographs, the Brookhaven team found it. In one image, a spray of tracks told a clear story when read carefully, and at the start of it was a particle with exactly the mass, charge, and strangeness Gell-Mann had described 2 years earlier. The omega minus was real. It sat precisely in the empty corner of the triangle, with close to the weight the pattern had demanded, like a missing puzzle piece dropped neatly into its slot. It is hard to overstate what this meant. A theory built purely from abstract symmetry, from the mathematics of patterns, had reached into the unknown and described a particle no one had ever seen, down to its specific properties, and nature had produced exactly that particle on demand. This is the highest thing a scientific idea can do. The eightfold way was not a coincidence and not a filing trick. It was telling the truth about how the particle world was built, but a successful pattern raises its own question, and Gell-Mann was already chasing it. Why should the particles fall into families of 8 and 10 in the first place? Why these shapes and not others? When numbers and patterns line up this neatly, there is almost always something physical underneath generating them, some simpler set of objects whose combinations naturally produce exactly these families. The symmetry was the shadow. Something was casting it. Think of it this way. If you found that every building in a city had a number of windows that was a multiple of 3, you would not call it magic. You would guess the windows came in panels of 3 and start looking for the panel. The eightfold ways families of 8 and 10 were too regular to be accidents. They had the fingerprint of an underlying unit, a small building block that, combined in a few simple ways, would generate precisely those patterns and no others. Gell-Mann did the mathematics and found that the families fell out perfectly if the particles were built from a small number of more basic pieces, combined 2 or 3 at a time. The 8s and 10s were not fundamental. They were the ways you could assemble a handful of deeper objects, the way the notes of a chord come from a few plucked strings. The particle zoo, the whole crowded swarm, could be built from just a few truly elementary things. There was a catch, and it was a strange one. For the arithmetic to come out right, these basic pieces had to carry electric charges that were fractions of the charge on a proton or electron, charges of 2/3 and 1/3. No one had ever seen a fraction of the basic unit of charge. Every particle ever measured carried a whole number of charges, never a piece of one. To explain the zoo, Gell-Mann was about to propose objects so odd that even he was not sure they were real. In 1964, Murray Gell-Mann proposed that the 8s and 10s of the Eightfold Way were built from just 3 basic pieces, combined in simple ways. A young physicist named George Zweig, working independently at the same time, arrived at the very same idea and called the pieces aces. Gell-Mann's name for them is the one that stuck. He called them quarks, a word he lifted from a line in James Joyce's novel Finnegan's Wake, where the phrase 3 quarks for muster mark appears in a stretch of dream language. He liked the sound, and he liked that there were 3. The scheme was elegant. The heavier particles, the ones in the families of 10, were each built from 3 quarks. The lighter mesons, like Yukawa's pion, were built from a quark paired with an antiquark, its mirror image partner. With just a few types of quark, combined 2 or 3 at a time, you could reproduce the entire crowded zoo. The proton, the neutron, the pion, the lambda, the omega minus, all of them were not fundamental at all. They were combinations, like words spelled from a tiny alphabet. To make this work, Gell-Mann needed 3 kinds of quark, which he labelled with plain names that carried no real meaning: up, down, and strange. The up quark and the down quark built the everyday matter of protons and neutrons. The strange quark carried that odd property of strangeness, and built the longer-lived particles that had puzzled everyone in the zoo. The omega minus, the particle that had just confirmed the Eightfold Way, turned out to be 3 strange quarks bound together, the heaviest, strangest corner of the pattern. The proton, in this picture, was 2 up quarks and 1 down quark. The neutron was 2 down quarks and 1 up. That small difference, swapping 1 quark for another, was the entire difference between the 2 particles that make up every nucleus. Change one up to a down and a proton becomes a neutron. It was a stunningly simple recipe for the heart of all matter, written in an alphabet of 3 letters. The strangeness of it lay in the charges. For the arithmetic of the proton to come out to a charge of exactly 1, the up quark had to carry a charge of positive 2/3, and the down quark a charge of negative 1/3. 2 ups and a down then add up cleanly. 2/3 plus 2/3 is 4/3. Take away 1/3 and you're left with exactly 1, the proton's charge. The neutron, 2 downs and an up, adds to 0, which is right since the neutron carries no charge at all. The fractions worked perfectly, but fractions of charge had never been seen. In every experiment ever done, electric charge came in whole units, the charge of 1 electron or 1 proton, never a sliver of it. You could have one charge or two charges, never 2/3 of a charge sitting on its own. Gell-Mann was proposing that the building blocks of all matter carried amounts of charge that no measurement had ever turned up loose in the world. It was the kind of claim that invites disbelief, and it got plenty. So Gell-Mann himself was careful, even cagey, about whether quarks were real things or just a useful trick. He sometimes spoke of them as a mathematical convenience, a way to organise the patterns and get the arithmetic right, without committing to the idea that you could ever find one. After all, if quarks were real particles, why had no one seen one, with its telltale fractional charge, in any detector? A real thing should be findable. A bookkeeping device need not be. This caution split the field. The quark model was undeniably powerful at sorting and predicting, yet its central objects seemed to be permanently hidden and impossibly charged. Were quarks the true bricks of matter, or just clever marks on a theorist's page? The only way to settle it was to look inside a proton directly and see whether anything was truly in there. That experiment was already being built, and it would fire electrons into protons hard enough to feel what lay within. To understand why so many physicists could not bring themselves to believe in quarks, you have to understand how sacred the unit of electric charge had become. Early in the 20th century, an American physicist named Robert Millikan had performed a famous delicate experiment. He sprayed tiny oil droplets into a chamber, gave them electric charges, and watched them float and fall between charged plates, measuring the charge on each one. Every droplet he measured carried a charge that was a whole number multiple of one basic amount. That basic amount was the charge of a single electron, and Millikan's result was taken as a deep law of nature. Charge was not smooth. It came in indivisible packets, like coins of a single denomination. You could have 1 packet or 7 packets or 1,000, but never 1/3 of a packet. This idea, that charge comes in whole units, was one of the bedrock facts of physics, confirmed again and again, woven into every theory. It felt as solid as anything in science. Now here was Gell-Mann and Zweig, proposing particles that carried 2/3 and 1/3 of that supposedly indivisible unit. To many physicists, this was not a small adjustment. It was an attack on something they were sure of. If quarks were real, then the basic packet of charge was not basic after all, and could be split into thirds, and yet those thirds somehow never appeared on their own. It strained belief in 2 directions at once. The pieces were impossibly small and impossibly hidden. So the search began for free quarks, loose ones carrying fractional charge, and it was taken seriously. Physicists looked everywhere a stray quark might hide. They examined cosmic rays, hunting for tracks that bent by the wrong amount for any whole charge. They ran careful versions of Millikan's oil drop experiment, looking for a droplet that carried 1/3 of a charge. They searched seawater and ancient rocks and moon dust, anywhere that quarks left over from the early universe might have settled. Nothing turned up. No one ever found a particle carrying a fraction of the basic charge, free and on its own. That failure cut 2 ways. To skeptics, it was proof that quarks were not real objects. If they were genuine particles, the reasoning went, then with enough energy you should be able to knock one loose and catch it, fractional charge and all. The total absence of free quarks suggested they were nothing more than a calculating device, lines in an equation that helped the patterns work out but did not correspond to anything you could hold or trap. Gell-Mann, for his part, kept a careful distance from the question. He used the quarks freely in his mathematics because they worked, while declining to insist they were physical things you could ever isolate. It was a sensible stance for a careful scientist. The model earned its keep by organising the zoo and predicting the omega minus, and that value did not depend on whether a single quark could ever be pried loose and examined. The arithmetic was real even if the objects were uncertain, but this left physics in an uncomfortable place. The most successful description of matter rested on objects that might or might not exist, carrying charges no one could find, hidden by a mechanism no one could explain. A theory cannot stay there forever. Either the quarks were real, and something deep was keeping them locked away, or they were fiction, and the patterns were a strange accident. The disagreement could not be settled by argument. It needed a direct look. The way to look was not to chase loose quarks across the sky and the seafloor, but to go straight into a proton and probe its insides. If a proton was a smooth, simple ball of charge, a beam fired into it would scatter one way. If it held hard little pieces, the beam would scatter another way entirely, the way Rutherford's alpha particles had bounced off the hard nucleus half a century before. The same trick that found the nucleus was about to be turned on the proton itself. The experiment that settled it was, in spirit, a repeat of Rutherford's, scaled up enormously. The idea was the same. To find out what is inside something, fire a small fast probe at it and watch how the probe scatters. If the target is soft and uniform, the probe passes through with only gentle deflections. If the target hides hard, concentrated pieces, the probe will occasionally bounce off at sharp angles, revealing the lumps within. Rutherford had used alpha particles and a thin gold foil. The new experiment would use electrons and a target of protons in the form of cold liquid hydrogen. The machine for it was built at Stanford in California, the Stanford Linear Accelerator Center, known as SLRC. Instead of a ring, it was a straight line, a tube 2 miles long, the longest such machine in the world, running under a road and across the landscape. Down that tube, electrons were driven to tremendous energies, faster and harder than any probe Rutherford could have dreamed of. The faster the electron, the smaller the detail it can resolve, and these electrons were fast enough to feel structure far smaller than a single proton. Through the late 1960s and into the early 70s, a team led by Jerome Friedman, Henry Kendall, and Richard Taylor fired these electrons into the hydrogen target and measured with great care how they came out. Most of the work was in the measuring. They recorded the angle and energy of the scattered electrons across many runs, building up a statistical picture of how the proton deflected the beam. A single bounce tells you little. Millions of them, sorted and counted, tell you the shape of what is inside. There were 2 ways the proton might behave. If the proton were a soft smeared ball of charge, with its electric charge spread evenly through its volume, then the hard, fast electrons would mostly pass through with small deflections, rarely bouncing back sharply. The charge would have nothing concentrated to push hard against the incoming electron. The pattern of scattering would be smooth and gentle, falling off quickly as the angle grew steep. But that is not what they found. Far more often than a smooth proton could explain, electrons came scattering out at large angles, kicked hard sideways and backward, as if they had struck something small and solid deep inside. The proton was not a soft ball. Just as Rutherford's rare bouncing alpha particles had revealed the hard nucleus, these hard scattered electrons revealed that the proton had hard pieces within it, tiny concentrated targets that could knock a fast electron clean off its path. The result was clear in the data, and it echoed the older discovery so closely that the meaning was hard to miss. Something small and dense lived inside the proton. The proton had structure. It was not a single smooth object, but a container holding sharper things, point-like as far as the experiment could tell, too small for the electrons to resolve any size to them at all. Whatever they were, they behaved like hard little points scattered through the proton's volume. This was a profound shift. For all the success of the quark model on paper, this was the first time anyone had reached into a proton and felt actual objects inside it. The patterns and the arithmetic had pointed to pieces, and now an experiment had bounced off those pieces directly. The question was no longer whether the proton had parts. It plainly did. The question was what those parts were, and whether they matched the strange fractionally charged quarks the theorists had proposed. The experimenters themselves were cautious at first about naming what they had hit. They had found hard points inside the proton, but calling them quarks was a leap the data did not yet force. It would take a theorist with a knack for plain pictures to give these inner objects a name, and to start building the bridge between the bouncing electrons at Stanford and the abstract quarks of Gell-Mann's equations. That theorist was Richard Feynman. Richard Feynman was one of the most original physicists of his time, famous for cutting through tangled mathematics to find the simple physical picture underneath. When he looked at the Stanford results, he did not start from the quark model and its symmetries. He started fresh from the bouncing electrons themselves and asked what the simplest possible picture of the proton's insides would be that could explain the data. His answer was deliberately humble and plain. He imagined the proton, when struck by a fast electron, as a loose bag of small pieces, and he gave those pieces a flat, non-committal name. He called them partons, simply meaning parts of the proton, with no claim about what they really were. This was a careful choice. By not calling them quarks, Feynman avoided assuming the answer. A parton was just whatever hard little object inside the proton the electron had bounced off. The name described the experiment, not a theory. The power of the parton picture was that it made the scattering easy to understand. When an electron strikes the proton at high energy, Feynman pictured it as not really hitting the proton as a whole, but striking one of the partons inside it, a single hard piece, while the others looked on. The electron ricochets off that one piece. Because the partons are point-like with no measurable size, they deflect the electron sharply, exactly the hard, wide-angle scattering the Stanford team kept seeing. A soft, smooth proton would never do that. A proton full of tiny hard points would do it naturally. This simple model made predictions about how the scattering should look as the energy and angle were varied, and those predictions matched the data. The way the proton deflected the beam followed a clean rule, a kind of scaling first worked out by the physicist James Bjorken, in which the pattern depended only on certain ratios and not on the raw energy. That clean behavior is exactly what you expect if the electron is bouncing off free, point-like pieces inside the proton rather than off a smeared-out hole. The partons were behaving like genuine, separate, hard objects. There was one detail in the picture that seemed paradoxical, and it would turn out to be the key to everything. Inside the proton, during that brief, violent moment of collision, the partons acted as if they were nearly free, barely held to one another, rattling around almost independently. The electron struck one, and that one absorbed the blow on its own, as though it were a loose marble rather than a piece tightly bound into the proton. The partons behaved as if the force holding them inside the proton had relaxed its grip. This was deeply strange, because the same partons could never be knocked out of the proton, no matter how hard the electron hit. They acted free inside, yet they were inescapably trapped. Hit one, and it would not come flying out as a loose particle. It stayed bound, even though, in the instant of impact, it had behaved as if nothing held it at all. Free up close, but caged. That contradiction sat at the centre of the parton picture, unexplained, waiting for a deeper theory. For the moment, though, the picture was a triumph of simplicity. Feynman had taken a confusing mass of scattering data and explained it with one homely image, a proton as a bag of small hard parts. The data and the picture fit so well that the existence of internal pieces was no longer in doubt. The proton had parts, point-like and hard, and they scattered electrons just as the picture said they would. The remaining task was to connect the two great threads of the story. On one side were Feynman's partons, the hard pieces bouncing electrons at Stanford. On the other were Gell-Mann's quarks, the abstract fractionally charged objects that organised the particle zoo. They had come from completely different directions, one from experiment and one from pure pattern. If they were the same thing, then the proton's parts had names and charges, and the quark model was not bookkeeping at all. It was a true map of what lay inside. The link between Feynman's partons and Gell-Mann's quarks turned on a few measurable details, and when physicists checked them, the two pictures locked together. The most telling clue was electric charge. If the partons inside the proton were really quarks, then they carried those strange fractional charges, 2/3 and 1/3 of the basic unit. That fractional charge would change how strongly each parton scattered the incoming electrons, because the electric force between two objects depends on their charges. When the Stanford data were analysed with this in mind, the numbers came out right for fractionally charged pieces. The way the proton's scattered electrons matched a proton built from objects carrying charges of 2/3 and -1/3, not from objects with whole charges. The very fractions that had seemed absurd, that had kept so many physicists from believing in quarks, were now showing up in the scattering, written into the angles and energies of the bouncing electrons. The partons were quarks, the quarks were real, and the count came out right too. The simplest reading of the proton was 3 quarks, 2 ups and 1 down, the recipe Gell-Mann had written from pure pattern. The proton at the centre of every atom was 2 up quarks and a down quark, bound together. The down quark and 1 up could swap roles to make a neutron. The matter of the everyday world, all of it, was built from just these 2 kinds of quark, arranged in 3s, exactly as the theory had said before anyone had ever felt them. This was the moment the quark stopped being a clever mark on a page and became a thing in the world. 2 completely separate lines of reasoning had met. From one direction came the abstract symmetry of the eightfold way, the families of 8 and 10, the predicted omega minus, the demand for fractionally charged building blocks. From the other came the brute experiment at Stanford, electrons fired into protons, bouncing off hard internal points. They pointed at the same objects, with the same charges, in the same numbers. When 2 such different paths arrive at one answer, the answer is almost certainly true. The recognition came in time, as recognition does. Friedman, Kendall and Taylor, the leaders of the Stanford experiment, received the Nobel Prize in 1990 for showing that the proton has structure, for the deep scattering that revealed the quarks inside. The fractional charges that no one had believed were now part of the foundation of physics. The proton had been opened, and inside it were the 3 quarks the pattern had promised. But the old paradox had not gone away, and now it was sharper than ever. The quarks were real, and they behaved inside the proton as if they were nearly free, rattling around almost loose during a collision. Yet no one had ever pulled one out. The searches through seawater and moon dust and cosmic rays had all come up empty, and they would stay empty. The quarks were genuine particles with measurable charges, and they were permanently trapped never to be seen alone. Both things were true at once, so the discovery of the quarks did not close the story. It reframed it around a single hard question. Why are quarks free up close but impossible to remove? What kind of force lets its pieces wander loosely when they are near one another, yet binds them so absolutely that no amount of energy can knock one out into the open? No ordinary force behaves that way. Gravity and electricity grow weaker with distance, and let their objects roam free if you pull hard enough. This force seemed to do the reverse. That question, the cage with no door, is the real heart of the strong force, and answering it would mean inventing a wholly new kind of charge and a wholly new theory to go with it. The quarks were real. Now physics had to explain the strangest prison in nature, one that holds its prisoners not by walls but by a force that grows stronger the harder you try to escape. Let me stay with this paradox, because it is one of the strangest facts in all of physics, and worth feeling fully before we resolve it. Quarks are real. We have bounced electrons off them and measured their fractional charges. They sit, 3 at a time, inside every proton and neutron in your body and in every star. And yet not one of them has ever been seen alone. No experiment, however violent, has ever produced a single free quark drifting on its own, with its telltale third of a charge. This is not for lack of trying. Physicists built ever more powerful machines through the second half of the 20th century, colliders that smashed particles together with energies far beyond anything Stanford had reached. The whole point of higher energy is to break things into their pieces. Hit a proton hard enough, the thinking goes, and surely you can shatter it and send its 3 quarks flying apart to be caught one by one. It is the natural expectation, and it is exactly what does not happen. When you slam 2 protons together at enormous energy, you do not get loose quarks. You get a spray of new particles, more protons and pions and other composite things, each one again made of quarks bound in groups, never a bare quark by itself. It is as if you tried to get one end of a string by cutting it, and every cut simply gave you two shorter strings, each with two ends. The quark you are trying to free is always wrapped up inside some new bundle. The door out of the proton seems not to exist. Compare this to every other force you know, and the oddness stands out. Pull an electron away from an atom, and with enough energy it comes free and flies off alone. In ordinary physics, if you supply enough energy, you can always pull two attracted things apart and end up with each of them on its own. The force between them weakens as they separate, and eventually it lets go. That is how forces are supposed to work. The force holding quarks does the opposite, and this is the crux. As you try to pull two quarks apart, the force between them does not weaken. It holds steady or even grows the way the pull of a stretched spring grows the more you stretch it. The harder you pull, the harder it pulls back, never relenting, never letting go. You can pour in as much energy as you like, and instead of the quarks coming free, that energy goes into the force itself, building up between them like tension in a stretched band. This behavior is called confinement, the permanent imprisonment of quarks inside the particles they build. It is not a practical limitation, not a matter of needing a bigger machine. As far as physicists can tell, it is a deep law of the strong force. A single quark cannot exist alone in the world. It can only exist bound up with others, hidden inside a proton or a neutron or one of their cousins, never stepping out into the open by itself. The cage has no door because the force makes one impossible, and yet in the same breath, we saw at Stanford that quarks inside the proton act almost free, rattling loosely when an electron strikes them. So the full puzzle has two faces that seem to contradict each other. Up close, inside the proton, the quarks barely feel the force and move nearly free. Far apart, when you try to separate them, the force becomes unbreakable. The strength of the strong force grows with distance, the reverse of everything else in nature. To explain a force that behaves so backward, physicists had to find a new property for the quarks to carry, a new kind of charge unlike electric charge, one that could grow stronger rather than weaker as things moved apart. That new charge, whimsically named for something we see every day, is the next piece of the puzzle, and it finally makes the strange behavior of the quarks make sense. The new kind of charge was forced on physics by a contradiction sitting inside the very particle that had confirmed the eightfold way, the omega minus. Recall that the omega minus is built from three strange quarks. The trouble is that quarks obey a strict rule that governs particles of their type, a rule that forbids two identical such particles from occupying the very same state in the very same place. It is the same rule that arranges electrons into shells and gives the chemical elements their structure. No two of these particles may be perfect copies in the same spot, yet the omega minus seemed to break it flatly. It held three strange quarks, all of the same kind, all packed into the same lowest energy state together, three identical particles where even two should have been forbidden. By the rules as they stood, the omega minus should not have been able to exist, but it plainly did. The particle that had so beautifully confirmed the quark patterns also seemed to violate one of the deepest laws governing the quarks themselves. The way out was to suppose that the three strange quarks were not truly identical after all. If each carried some new property, a label that came in three varieties, then the three quarks could each take a different label, and so avoid being perfect copies. The rule would be satisfied. There had to be a hidden threefold property, a new kind of charge that quarks carried in addition to their electric charge, with three possible values instead of the simple plus and minus of electricity. Physicists, with their fondness for playful names, called this property colour. It has nothing to do with real colour, nothing to do with light or sight. The name is a convenient picture, chosen because the three values combine in a way that recalls how three primary colours of light combine. The three values were labelled red, green and blue, again purely as names. A quark carries one of these three color charges, and that is the new property that keeps the three strange quarks in the omega- from being identical. The picture has a satisfying rule built into it. Just as red, green and blue light together make white, a proton or neutron is built from one quark of each color, and the three colors together make the particle colorless overall. Nature only allows colorless combinations to exist freely. Three quarks of three different colors make a colorless particle like the proton. A quark and an antiquark, carrying a color and its matching anticolor, make a colorless particle like the pion. You never get a leftover color showing. This rule, that only colorless combinations can exist on their own, is the deep reason for confinement. A single quark carries a color, so it is not colorless, and so it cannot exist alone in the world. To be free, an object must be color neutral, and one quark never is. The quarks are forced to clump into colorless groups precisely because a lone color is forbidden. The cage with no door is, at bottom, a rule about color. A bare color charge simply may not roam free. The first hints of this idea came from a few physicists working on the omega- problem and related puzzles, among them Oscar Greenberg, and later Mu Young Han working with Yoichiro Nambu, who built the threefold scheme more fully. At first, color looked like another piece of bookkeeping, a label invented to save a rule. But it would prove to be far more. Color was the actual charge of the strong force, the thing the force responds to, the way electric charge is the thing the electric force responds to. That step is the doorway into the real theory of the strong force. Electric charge has the photon as its carrier and electricity as its force. If color is a charge, then it too should have carriers, particles passed between coloured quarks to bind them, and a full force built on colour. Those carriers turned out to be a new set of particles, 8 of them, with a property so strange that it makes the strong force behave like nothing else in nature. They are called gluons, and they are where we go next. All chapters land in range with no stray dashes. Let me clear the discouraged words, actually, honestly. We left off with a new charge, colour, that quarks carry, and the rule that only colourless combinations can exist on their own. But a charge by itself does nothing. Electric charge would mean nothing without the photon to carry the electric force between charges. So if colour is real, there must be carriers too, particles that pass between coloured quarks and bind them. Those carriers are the gluons, and the name is plain. They are the glue. A gluon is in some ways a cousin of the photon. Like the photon, it has no mass, so on its own it would travel at the speed of light. Like the photon, it carries a force between particles that hold the matching charge. The photon binds electric charges into atoms. The gluon binds colour charges into protons and neutrons. Where the electric force is built on one kind of charge, plus and minus, the strong force is built on 3 colours, and the gluons are the messengers that connect them. But here the resemblance breaks, and the break is everything. There is only one kind of photon, and it carries no electric charge of its own. The gluon is different. Because colour comes in 3 values, the gluons that shuttle colour between quarks must themselves carry colour, in combinations of a colour and an anticolour. Work through the possible combinations and you find not one gluon but 8 distinct carriers, each carrying its own mix of colour and anticolour. The strong force speaks in 8 voices where electricity speaks in 1. Picture what a gluon does inside a proton. A quark of one colour emits a gluon and in doing so changes its colour. The gluon carries that colour away and is absorbed by another quark, which takes on the colour in turn. The quarks inside the proton are constantly trading gluons, constantly swapping colours back and forth, a blur of exchange far too fast to follow. A red quark passes a gluon and becomes blue. The quark that catches it turns red. The colours flicker and shift endlessly, but at every instant the proton as a whole stays colourless, one of each colour balanced together. This ceaseless trading is the strong force in action. The binding that holds a proton together is not a single steady pull, but a storm of gluons flying between the quarks, billions upon billions of exchanges, holding the three quarks in their colourless bundle. It is far busier than the calm orbit of electrons around a nucleus. Inside the proton, the gluons are everywhere, carrying colour, binding the quarks, and as we'll see, doing something no photon ever does. The number 8 is not arbitrary, and it is worth pausing on. It comes straight out of the mathematics of three colours, the same mathematics that gave the eightfold way its families of 8. When Gell-Mann sorted the particles into octets, he was seeing the shadow of this same threefold symmetry from the outside. Now, inside the proton, the symmetry shows itself directly, in 8 gluons carrying colour between 3 kinds of quark. The pattern that organised the zoo and the force that binds the proton spring from the same root. So the picture has filled in. Quarks carry colour, 3 values of it. Gluons, 8 of them, carry colour between the quarks and bind them into colourless protons and neutrons. The strong force is the trading of gluons, just as the electric force is the trading of photons. It looks at this stage like a clean parallel to electricity, only with more colours and more carriers. It is not a clean parallel, and the reason is the single strangest feature of the strong force. The gluons carry colour, which means they feel the very force they carry. A gluon can pull on another gluon. The glue sticks to itself, and that one fact, simple to state, is what makes the strong force behave like nothing else in nature. Sit with the strange fact from the last chapter, because the whole behaviour of the strong force grows out of it. The photon, the carrier of electricity, has no electric charge. Light does not pull on light. 2 beams crossing an empty space pass straight through each other, without the slightest interaction, because a photon is blind to the charge it carries to others. This is why electricity is, in a sense, simple. The carrier stays out of the way. The gluon is not blind. It carries colour charge, the very thing the strong force responds to. So a gluon pulls on other gluons. The carriers of the strong force feel the strong force themselves. This sounds like a small technical difference, a footnote in the bookkeeping. It is the hinge on which everything turns, and it makes the strong force a tangled, self-feeding thing where electricity is a tidy one. Think about what it means for the field between 2 quarks. With electricity, the field lines between 2 charges spread out into space, fanning apart, growing thinner and weaker with distance. That spreading is why the electric force fades as charges move apart. The photons carrying the force do not clump together, so the field simply dilutes. Pull 2 charges apart and the pull between them dies away smoothly. Now do the same with 2 quarks bound by gluons. The gluons between them carry colour, so they attract one another. Instead of spreading out and thinning, the gluon field pulls itself inward into a tight, narrow tube running directly between the 2 quarks. The lines of force do not fan out into space, they gather into a chord. The self-attraction of the gluons squeezes the field into a narrow channel, and that channel is the secret behind why quarks can never escape. This single property, that the glue sticks to itself, explains the 2 great mysteries we have been carrying. First, it explains why the force grows stronger as quarks move apart, the opposite of every familiar force. Because the field is bound into a tube of roughly fixed thickness, rather than fanning out. Pulling the quarks farther apart does not thin the force. It just makes the tube longer, and a longer tube holds more energy, so the pull stays strong no matter how far you stretch it. Second, the same self-attraction means that up close, where the quarks are nearly on top of each other, the tangle of gluons largely cancels and the force grows weak, which is why the quarks at Stanford acted almost free. It is hard to overstate how unusual this makes the strong force. Every other force in nature weakens as its objects separate and strengthens as they close in. The strong force does the reverse at long range, holding firm or growing as quarks part, all because its carrier is not a neutral bystander, but an active participant that binds to itself. A force whose messengers shout to one another, behaves in ways a force of silent messengers never could. This self-interaction also makes the strong force fiendishly hard to calculate. With electricity, you can treat the force as a series of small, clean steps, each photon exchange a tidy correction on the last. With the strong force, the gluons spawn more gluons, which spawn more still, all pulling on one another, and the simple step-by-step method breaks down. The math turns from a clear stream into a churning rapid. Much of the difficulty of understanding the proton comes straight from this one fact about the gluon. So the gluon carrying colour is not a footnote, it is the engine. It bends the field into a tube, it flips the force to grow with distance, it frees the quarks up close, and it makes the whole thing nearly impossible to compute. To turn this picture into a real, working theory, physicists needed a mathematical framework built to handle exactly this kind of self-interacting force. That framework had been sitting on a shelf, half ignored for nearly 20 years. The mathematical framework the strong force needed had been written down in 1954, long before anyone knew about colour or gluons, by two physicists at Brookhaven, Chen-Ning Yang and Robert Mills. They were trying to generalise the theory of electricity into something richer. Ordinary electromagnetism is built on a symmetry, a rule that you can shift the description of a charged particle everywhere at once without changing any physics. Yang and Mills asked what would happen if you demanded that the shift could be different at every point in space, a far stricter requirement. When they worked it out, something remarkable fell out of the mathematics. To keep the physics unchanged under such a local point-by-point symmetry, the theory was forced to contain force-carrying particles, and those carriers had to interact with one another. The structure demanded self-interacting carriers, the very thing the gluons turned out to be. Yang and Mills had built, in pure mathematics, the kind of theory the strong force would need, but at the time there was no force it obviously described, and the idea sat mostly unused for years. What was missing was the right charge to hang the theory on. The Yang-Mills construction is a template. It says, give me a charge with a certain symmetry, and I will give you the carriers and the force. For nearly 2 decades, no one had the right charge to feed it. Then colour arrived, a charge with exactly 3 values and exactly the 3-fold symmetry the template could use. The lock had been waiting, and colour was the key. In the early 1970s, a few theorists fit the two together. Harold Fritsch and Murray Gell-Mann, working with Heinrich Leutwiler, took the Yang-Mills template, fed it the 3-valued colour charge, and out came a complete theory of the strong force. The quarks carried colour. The gauge symmetry of colour forced exactly 8 self-interacting carriers, the gluons. The whole structure, quarks, colours, 8 gluons, and their tangled self-interaction followed from a single symmetry principle. The guesswork of the previous decade became a theory with real foundations. They gave it a name with a Greek flavour, quantum chromodynamics, where chromo means colour. It is usually shortened to its initials. The name sits deliberately beside the older theory of electricity, quantum electrodynamics, the supremely successful theory of how charged particles and photons behave. Chromodynamics was meant to be its sibling, the theory of colour and gluons standing next to the theory of charge and photons. 2 great quantum theories of force, one for the electric world we see, and one for the colour world hidden inside the proton. But chromodynamics had a feature its older sibling lacked, the self-interacting carriers, and that feature made it both stranger and in one way more beautiful. Everything peculiar about the strong force, the confinement of quarks, the tube of field between them, the freedom up close, was now contained in one compact set of rules. The theory did not have to assume confinement or bolt it on by hand. In principle, all of it should follow from the single fact that colour obeys a Yang-Mills symmetry. The behaviour was supposed to be baked in. That word supposed matters, because writing the theory down was not the same as proving it worked. The self-interaction that made chromodynamics powerful also made it brutally hard to solve. The equations were clear, but extracting predictions from them, especially at the low energies where quarks bind into protons, was beyond what anyone could calculate by hand. The theory was elegant on paper and nearly intractable in practice. So the immediate question was whether chromodynamics could explain the one thing that had launched the whole search, the behaviour seen at Stanford, where quarks acted free inside the proton. If the theory could show, from its own equations, why a force that traps quarks forever would also let them rattle loose up close, that would be its first great test. The answer came in 1973, and it was so surprising that at first, the physicists who found it could hardly believe their own result. The test of the new theory came down to a single question. How does the strong force change as quarks move closer together or farther apart? Every force physicists knew weakened with distance and strengthened up close. The puzzle at Stanford was that the quarks inside the proton behaved as if the force nearly vanished when they were close, even though it trapped them forever when far apart. If quantum chromodynamics was right, its equations would have to produce this backward behaviour on their own. In 1973, two groups attacked the problem. At Princeton, a young professor named David Gross and his graduate student Frank Wilczek did the calculation. Independently, a graduate student at Harvard named David Politzer did the same. They were computing how the strength of the strong force changed with distance, a quantity that, in any ordinary theory, grows as things get closer. They expected the strong force to do what every other force did. The result came out with the opposite sign. The calculation said the strong force grows weaker as quarks get closer and fades toward nothing at the very shortest distances. Up close, almost no force. This was the reverse of electricity, the reverse of intuition, the reverse of what these very physicists expected to find. Gross had set out partly to show the idea could not work, and the mathematics told him it did. The property was so strange it was given a name that sounds like a contradiction: asymptotic freedom. As quarks approach, they become asymptotically free, barely bound at all. Here was the explanation for Stanford, falling straight out of the theory. When a fast electron strikes a quark deep inside the proton, it probes the quark at very short distance, and at short distance the strong force has faded almost to nothing. So the struck quark recoils as if it were free, rattling loose, absorbing the blow on its own. The quarks act free up close not because nothing binds them, but because the binding force itself switches off as they draw near. The theory predicted exactly the freedom the experiment had seen, and the same mathematics carried the other half of the story. If the force fades to nothing at short distance, it must grow as the distance increases. The strength runs the other way as quarks separate, climbing instead of falling. This is the confinement we kept meeting, now emerging from the equations rather than assumed. A force that weakens to zero up close and strengthens without limit far away is precisely a force that lets quarks jiggle freely inside the proton, yet never lets them leave. Both mysteries, the freedom and the cage, were two ends of the same curve. The root of it, once again, was the gluon self-interaction. In an ordinary theory, the cloud of activity around a charge screens it, softening the force at a distance and sharpening it up close. In chromodynamics, the gluons pulling on one another do the opposite. Their self-interaction spreads the colour charge's influence outward, so the force builds with distance and thins to nothing at the core. The strange sign in the calculation traced directly back to the glue sticking to itself. Asymptotic freedom was a turning point. It showed that quantum chromodynamics was not just an elegant guess, but a theory that could reproduce, from first principles, the behaviour really seen in the laboratory. The freedom of quarks up close was no longer a mystery to be explained, but a prediction the theory made. Chromodynamics had passed its first hard test, and the strong force finally had a description that worked from the inside out. The importance of the discovery was recognised decades later, when Gross, Wilczek, and Politzer shared the Nobel Prize in 2004 for asymptotic freedom. By then, chromodynamics had been confirmed in countless experiments and stood as one of the pillars of physics. But in 1973, the deepest consequence of the discovery was still being worked out. the strange picture of what really happens when you try to pull a single quark out of a proton. Let me make the running strength of the strong force concrete, because it is the heart of why a proton holds together and why a quark can never leave. We're used to forces that fade. Move two magnets apart and the pull drops away fast. Step back from a fire and the warmth thins. The world runs on forces that grow gentle with distance, and our intuition is built on them. The strong force violates that intuition completely. Imagine two quarks inside a proton, close together. At that tiny separation, asymptotic freedom has nearly switched the force off, and the quarks drift almost free as the Stanford electrons found. Now begin to pull them apart. As the gap widens, the force between them does not weaken. It holds firm, steady, and as you keep pulling it grows. The farther apart the quarks, the harder the strong force tugs them back. You're fighting a pull that strengthens the more ground you take. The reason lies in the gluon field running between them. Because the gluons attract one another, the field does not spread out into space. It collapses into a narrow tube of force connecting the two quarks, a cord of pure, strong force energy. As you draw the quarks apart, you do not stretch the field thinner. You make the tube longer, and a longer tube simply contains more energy along its length. The pull comes from the tension in that cord, and like the tension in a stretched rubber band, it does not relent as you stretch it. If anything, you're loading more and more energy into the connection. Think of the difference this way. Pulling apart two electric charges is like separating two objects joined by a slack thread that frays and snaps and leaves them free. Pulling apart two quarks is like stretching an unbreakable elastic cord that only stores more energy the more you pull. The electric thread releases its grip. The strong cord tightens its hold. One lets go, the other never does. This is why pulling quarks apart only feeds the force. Every bit of energy you pour into separating them goes straight into the tube of gluon fields stretching between them. You're not loosening the bond. You're charging it, pumping energy into the cord like winding a spring tighter and tighter. The strong force takes everything you give it and stores it as tension, growing more determined to snap the quarks back together the harder you try to part them. And there is a limit to how far this can go, though not the limit you would expect. You might think that with enough energy you would finally overpower the force and tear a quark free. But the energy you have been pouring into the tube does something else entirely. Long before the tube can stretch far enough to release a lone quark, it holds so much energy that the energy itself turns into new matter, and the cord snaps in a way that produces not a free quark but fresh particles. The escape you are attempting becomes instead an act of creation. That is the deep resolution of the cage with no door. You cannot remove a quark by pulling, because pulling only stores energy in the bond, and that stored energy, when it is great enough, becomes new quarks rather than freeing the old one. The harder you try to isolate a quark, the more the force conspires to keep all quarks bundled into colourless groups. The prison is not a wall, it is a force that turns your every escape attempt into more prisoners. To see exactly how the cord snaps, and why the result is always new bound particles and never a lone quark, we need to look closely at the tube of gluon field itself, the unbreakable string running between the quarks, and watch what happens at the moment it breaks. Picture the tube of gluon field between two quarks as a string, a taut cord of strong force energy. Physicists call it a flux tube, and the picture is more than a metaphor. The gluon field really does gather into a narrow channel between coloured quarks, with a roughly constant amount of energy packed into each length of it. Double the length of the string, and you roughly double its energy. This even loading is what gives the strong force its steady, unrelenting pull. There is a definite figure attached to this tube, and it gives a sense of just how much energy is involved. The string between two quarks holds something like a ton's worth of pulling force, concentrated in a channel far thinner than a single proton. To stretch it by even a tiny distance takes enormous energy. This is not a gentle bond. It is one of the most powerful tensions in nature, packed into the smallest of spaces, and it is what you are fighting when you try to separate a quark from its partners. Now watch what happens as you pull. The string stretches and stores energy, more and more of it, the tension never easing. At some point, the energy stored in the stretched string becomes as large as the energy locked in the mass of a quark and an antiquark together. Recall the famous equation, energy equals mass times the speed of light squared. It runs in both directions. Enough energy, concentrated in a small enough place, can become matter. The strained string holds exactly that much energy in exactly such a place. So the string does not snap to leave a bare quark at each end. Instead, at the moment of breaking, the stored energy turns into a fresh quark and antiquark, born right there in the middle of the cord. The string breaks into two shorter strings, and each new end is capped by one of the newly created particles. You pulled to separate two quarks, and the energy of your pulling simply made two more quarks to fill the gap. Where you had one string, you now have two, each still bound, each still colourless. This is why you can never end up with a lone quark. Cut the string, and the cut heals itself by creating new quarks at the fresh ends. The way snapping a magnet in half gives you two whole magnets, each with its own north and south, never a single isolated pole. Every attempt to expose a free end produces a new particle to cover it. The quark you wanted to free is always paired with a partner conjured from the energy you supplied. The cord is, in this sense, truly unbreakable. You can break the string, but you can never break the rule. This single mechanism is confinement made vivid. The reason no one has ever caught a free quark, despite all the searches through seawater and moon dust, and the most violent collisions ever staged, is that the strong force will always spend your energy on making new quarks, rather than releasing an old one. The more violently you strike a proton, the more new particles you create, and every one of them comes out as part of a colourless bundle. The strong force guards its rule absolutely. Colour stays hidden, always, inside neutral combinations. It also tells us where new particles come from in a collision. When physicists smash protons together at great energy, the quarks inside are briefly knocked apart, strings of gluon fields stretch between them, and those strings snap into showers of fresh quarks and antiquarks, which gather into new protons, pions, and the rest. The spray of particles pouring out of a collision is the strings breaking over and over, turning collision energy into matter. That spray is not just theory. In a particle detector, it appears as a striking, visible pattern, narrow jets of particles fanning out from the collision point, and those jets are the closest thing we will ever see to a quark caught in the act of trying to escape. When a quark is knocked hard out of a proton in a collision, it does not fly off alone because it cannot. As it speeds away, the string of gluon fields stretching behind it snaps again and again, each break making new quarks and antiquarks, and these gather into a tight, fast-moving spray of ordinary particles all heading in nearly the same direction. Physicists call this spray a jet. The original quark is gone, hidden inside the shower, but the jet points back along the path the quark took. This process of turning loose quarks into sprays of bound particles has a name, hadronization, since the bound particles, protons and pions and their kin, are together called hadrons. Hadronization happens in the briefest instant after a collision, far too fast to watch directly, as every freed quark dresses itself in a cloak of new particles before it can ever appear alone. What enters the detector is never a quark, it is the jet, the crowd of hadrons the quark's escape attempt created. So the jets are the visible signature of confinement. You cannot see a quark, but you can see the spray it leaves behind, and the shape of that spray carries the quark's fingerprint, its direction, and its energy written into the collective motion of the particles. When physicists study jets, they are reading the tracks of quarks and gluons indirectly, the way you might know a fast animal had passed by the dust it kicked up, never glimpsing the animal itself. The jet is the dust of a vanished quark. This gave physicists a way to test the theory, and even to see the gluon. If quarks produce jets, then a gluon, knocked loose with enough energy, should produce a jet of its own. In 1979, at a laboratory in Hamburg, Germany, experiments at a collider called Petra found events with 3 jets instead of the usual 2. 2 jets came from a quark and an antiquark flying apart. The 3rd jet was the telltale mark of a gluon, radiated by one of the quarks and then hadronizing into its own spray. It was the first direct evidence that the gluon was real. That 3-jet pattern was for the gluon what the bouncing electrons had been for the quark, a way of seeing the unseeable through its effects. The gluon, like the quark, can never be caught alone, since it too carries colour and must hide inside colourless bundles. But its jet betrays it. By counting jets and measuring their shapes and how often 3 appeared instead of 2, physicists confirmed not only that gluons exist, but that they behave just as quantum chromodynamics says, carrying the strong force and radiating from quarks at the rates the theory predicts. Today, jets are everywhere in particle physics. At the largest colliders, where protons are smashed together billions of times, the detectors fill with jets, sprays of hadrons marking the quarks and gluons that briefly broke free before the strong force reclaimed them. Reading those jets is daily work, the standard way of studying what happened in a collision. Every jet is a small confirmation of confinement, a quark or gluon that tried to leave and was wrapped in an instant in a coat of new matter. There is something almost poetic in it. The strong force will never let us hold a quark in our hand, never let us isolate one of the true building blocks of matter. But in forbidding that, it shows itself plainly in the sprays of particles that pour from every high-energy collision. We see the strong force precisely in its refusal, in the way it turns escape into creation. The jets are confinement caught in the act. And all of this, the jets, the strings, the trapped quarks, the gluons binding them, leads back to the question we started with, the weight in your hand. For hidden in this furious activity inside the proton is the answer to where almost all of its mass really comes from. Now we can finally answer the question we began with. A proton is 2 up quarks and 1 down quark. Weigh those 3 quarks on their own, add up the small masses the up and down quarks carry, and you account for only about 1 part in 100 of the proton's total mass. 1%. The other 99% is not in the quarks at all. It is in the strong force binding them, in the energy of the gluon field and the restless motion of the quarks within it. Remember the equation that has been waiting in the background the whole time. Energy equals mass times the speed of light squared. It means energy and mass are the same thing measured 2 ways. Anything that carries energy has mass, and anything with mass carries energy. Inside the proton, the strong force is a storm of energy, gluons flying between quarks, the field tense with the unbreakable strings, the quarks moving at nearly the speed of light. All that energy, trapped inside the proton, has mass, and it is almost all the mass there is. Picture it this way. The 3 quarks are like 3 tiny seeds rattling inside a churning energetic field. The seeds themselves weigh almost nothing, but the field they live in, the gluons binding them, the violent motion they are forced into, holds a tremendous amount of energy in a tiny space, and that trapped energy is what your scale reads when you weigh the proton. The mass of the proton is mostly the mass of confinement itself, the weight of a force locked into a box too small to see. This is one of the deepest and least known facts in all of physics. The mass of nearly everything around you, the chair, the table, the planet, your own body, is not the mass of solid stuff. It is the energy of the strong force, made heavy by the bridge between energy and mass. When you feel the weight of an object in your hand, you are feeling almost entirely the bottled energy of gluon fields churning inside countless protons and neutrons. The heft is the force, not the matter. It is worth letting that settle because it overturns the natural picture of weight. We imagine mass as a measure of how much stuff a thing contains, as if heaviness meant more material packed in. But at the deepest level, the stuff, the actual quarks, contributes almost nothing to the weight. The weight comes from energy held in place, from motion and binding and field. Mass for ordinary matter is mostly trapped energy wearing the disguise of solidity. The proton, then, is less like a bag of marbles and more like a sealed box humming with energy. Open it, and you would not find 3 heavy balls. You would find 3 nearly weightless specks and an enormous amount of energy roaring between them, energy that cannot escape, energy that the world outside reads as mass. The proton weighs what it weighs because the strong force traps that much energy in that smaller space. Confinement does not just hold the quarks, it is what makes them heavy, what makes you heavy. So the answer to our opening question is in hand. What gives the proton its mass is not the matter inside it, but the strong force itself, the energy of the gluon field bound up by confinement and turned into weight. The thing you held at the very start, the coin or the key or the stone, is heavy almost entirely because of a force you cannot see, locked inside particles you cannot reach. The weight in your hand is the strong force made manifest. But there is a piece still missing. We said the quarks themselves carry a small mass, that leftover 1%. Where does even that come from? That sliver has a different origin entirely, one tied to a famous particle, and a different field filling all of space, and it is worth seeing clearly so as not to confuse it with the strong force at all. The small remainder, the roughly 1% of the proton's mass that does come from the quarks themselves, has nothing to do with the strong force. It comes from somewhere else entirely, from a field that fills all of space, and a particle that became famous in 2012, the Higgs. To understand the proton fully, you have to keep these 2 sources of mass apart because they are constantly confused, and they could hardly be more different. The Higgs field is thought to fill the whole universe, an invisible presence everywhere at once. Certain fundamental particles, as they move through it, are slowed by their interaction with this field, and that resistance shows up as mass. A particle that interacts strongly with the Higgs field is heavy. One that barely interacts is light. The electron gets its small mass this way. The quarks get their rest masses this way too. The Higgs is the origin of the intrinsic mass of the basic building blocks, the mass they carry on their own, apart from any force binding them. When the Higgs particle was discovered at the Large Collider near Geneva, it was rightly celebrated as the confirmation of where fundamental mass comes from. Headlines called it the origin of mass, and for the fundamental particles, that is fair. The quark's own small mass, the electron's mass, the masses written into the basic table of particles, all traced to the Higgs field. Without it, those particles would be massless, and the universe would look nothing like it does. But here is the crucial point. The mass the Higgs gives the quarks is tiny. The up and down quarks that build the proton are extraordinarily light, and their combined Higgs-given mass adds up to only that 1% of the proton. If the Higgs field were the whole story of mass, a proton would weigh almost nothing, and so would you. The Higgs explains the mass of the quarks, but the quarks are nearly weightless. It does not explain the mass of the proton, which is the mass that truly matters for the weight of the everyday world. That mass, the other 99%, comes from the strong force, exactly as we have seen. So the everyday weight of matter has 2 sources, wildly unequal in size. A sliver comes from the Higgs field, giving the quarks their small intrinsic mass. The vast bulk comes from quantum chromodynamics, from the energy of confinement bound inside each proton and neutron. When you feel the weight of an object, you're feeling, to about 1 part in 100, the Higgs, and for all the rest, the strong force. This is why it is misleading to call the Higgs the origin of mass without qualification. It is the origin of the fundamental particle's mass, but almost all the mass you encounter, almost all the mass of the visible universe, is not Higgs mass at all. It is strong force energy. The stars, the planets, the mountains, your body, weigh what they weigh overwhelmingly because of the energy trapped by the strong force, not because of the Higgs field. The famous particle accounts for the small part. The hidden force accounts for nearly everything. Keeping the 2 straight clears up one of the most common confusions about modern physics. The Higgs and the strong force are both sources of mass, but they work in completely different ways and on completely different scales. The Higgs slows fundamental particles through a field in space. The strong force traps energy inside the proton through confinement. One gives the quarks their feather-like rest mass. The other turns the proton into the heavy object that gives the world its weight. With both pieces in place, the proton looks almost complete. 3 quarks, like from the Higgs, bound by gluons whose trapped energy is nearly all the weight. But the simple picture of 3 tidy quarks is, it turns out, far too calm. Look closer inside the proton, and you find not 3 quiet particles, but a roiling, seething sea. The picture we have built, a proton as 3 quarks bound by gluons, is true but tidy, and the inside of a real proton is anything but tidy. The 3 quarks we keep naming, the 2 ups and the down, are only the permanent residents, the ones that give the proton its identity and its charge. They are called the valence quarks, but they are not alone in there. Around them churns a wild, constantly changing crowd of other particles, appearing and vanishing too fast to count. This crowd comes from the gluons. A gluon flying between the valence quarks can, for a fleeting instant, turn into a quark and an antiquark, which then annihilate back into a gluon almost as soon as they appear. The strong force is so intense inside the proton that this is happening everywhere, all the time. The energy of the field is constantly congealing into brief pairs of quarks and antiquarks and dissolving again. These short-lived particles are called the sea, and the proton is full of them. So if you could freeze a proton and look inside, you would not see 3 quarks sitting quietly. You would see 3 valence quarks embedded in a boiling sea of gluons and of quark-antiquark pairs flickering in and out of existence. A storm of activity with no still moment anywhere in it. The proton is less a small solar system of 3 orbiting bodies and more a churning droplet, dense with transient matter, seething with the energy of the strong force. The calm 3-quark sketch is a long exposure photograph of something that never holds still. This sea is not a minor detail. When the electrons at Stanford and later experiments probed the proton at higher and higher energy, looking ever more closely, they found more and more of these sea quarks and gluons carrying the proton's energy and momentum. The deeper you look, the more crowded the proton appears. At the finest resolution, the 3 valence quarks are almost lost in a swarm of fleeting pairs and a thick haze of gluons. What looked like 3 particles becomes an ocean. The sea even contains, briefly, heavier kinds of quark that are not among the proton's permanent residents at all. For an instant, the energy of the field can conjure a strange quark and its antiquark, or even heavier types, before they vanish again. So a proton is not purely made of up and down quarks. It is made of up and down valence quarks, plus a shifting sea that momentarily holds every kind of quark nature allows, each flickering into being on borrowed energy and paying it back almost at once. The proton contains, in passing, a sample of the whole quark family. All of this churning is still bound by the same rules. Through every flicker of the sea, the proton as a whole stays colourless, its charge stays exactly 1, and its mass holds steady at the value set by the trapped energy of the whole roiling system. The chaos inside is real, but it is chaos in service of a stable whole. The proton is one of the most stable objects in the universe, and yet inside it nothing is ever still. Stability on the outside, a storm on the inside. This is the truer picture of the proton, and it is stranger and richer than the simple 3-quark model that got us here. The proton is not a static little knot of 3 particles. It is a dynamic, seething system, mostly energy, mostly motion, with 3 persistent quarks riding a sea of transient ones, all held together by the self-tangling strong force. The weight in your hand is the weight of that storm, repeated across every proton in the object, and the storm holds at least one more surprise, a puzzle that physicists are still working through today. It concerns something simple that the proton has, and that ought to be easy to account for, its spin. When physicists try to add up where that spin comes from, the numbers refuse to work, and the shortfall is one of the live mysteries of the proton. Every proton has a property called spin. You can picture it loosely as the proton turning like a tiny top, carrying a fixed amount of rotational motion that never changes. Spin is one of the proton's basic defining features, as fundamental as its charge. And for a long time, the source of that spin seemed obvious. The proton is made of 3 quarks, each of which carries its own spin, so surely the proton spin is just the 3 quark spins added together. 2 pointing one way, 1 the other, and the sum is the proton spin. Simple. In the late 1980s, an experiment at the large laboratory near Geneva set out to confirm this tidy accounting by measuring how much of the proton spin the quarks really carry. The expectation was that the quark spins would supply essentially all of it. The result was a shock. The spins of the quarks added up to only a small fraction of the proton's total spin, far less than expected, perhaps only 1/4 to 1/3 of it. The other 2/3 or more was simply missing from the count. This became known as the proton spin puzzle, or the spin crisis, and it caught the field off guard. The proton spin is a definite measured quantity. The quarks were supposed to account for it, and they did not come close. Most of the proton spin was coming from somewhere other than the spins of its 3 valence quarks. Once again, the proton had refused to be simple, and once again the missing piece pointed into the churning interior we had only just begun to appreciate. The resolution, as far as physicists can now tell, lies in the rest of that interior, the parts beyond the 3 valence quark spins. The gluons carry spin of their own, and there are a great many of them, so their spins contribute to the total. The C quarks contribute as well, and there is another source, the orbital motion of the quarks and gluons, the way they circle and move within the proton, which carries rotational motion just as a planet orbiting the Sun carries motion quite apart from its own spin. The proton spin is built from all of these together, so the proton spin is not a simple sum of 3 quark spins but a budget with several contributors: the quark spins, the gluon spins, and the orbital motion of everything inside. Adding them all correctly is extraordinarily difficult, because it means accounting for the entire roiling sea and the swirling motion within it, not just the 3 permanent quarks. Measuring each piece is the work of major experiments running today, and the full accounting is not yet complete. This is a place where it is honest to say the picture is still unfinished. Physicists are confident the spin must add up in the end, that the quark spins, the gluon spins, and the orbital motions together make the whole. But pinning down exactly how much each part contributes is hard, ongoing work, with experiments at several laboratories still measuring the gluon and C contributions, and the orbital piece hardest of all to capture. The proton keeps its books, but reading them in full has taken decades and is not done. It is a fitting puzzle for the proton, an object that hides almost all of its mass in a force we cannot see, and almost all of its spin in motion we are still learning to measure. The simple proton, 3 quarks and done, dissolves the moment you look closely, replaced by something far harder and far more interesting. Even its spin, a thing as basic as a spinning top, turns out to be a deep and partly open question. To pin down the proton at all, to measure its size and its properties precisely, physicists have had to push their experiments to extraordinary delicacy, and even then the proton has thrown them a surprise about something as basic as how big it is. You might think that measuring the size of a proton would be settled, routine, long since pinned down to many decimal places. The proton is the most studied particle in physics, and for years its radius was known, measured in 2 independent ways that agreed, a number a little less than 1/4 of a meter across. A 1/4 of a meter is called a femtometer, and the proton's radius came out to roughly 88/100ths of a femtometer. 2 methods, 1 answer. Settled, it seemed. The first method measured the proton's size by firing electrons at it and studying how they scattered, the same scattering tradition that goes back to Rutherford and Stanford, refined to extract the proton's radius from the pattern. The second method used ordinary hydrogen, a single electron orbiting a single proton. The electron's energy levels depend very slightly on the size of the proton it orbits, so measuring those levels with great precision reveals the radius. Both methods landed near the same value, and physicists were satisfied. Then, in 2010, a group tried something cleverer and got a different answer. They made a special kind of hydrogen, replacing the orbiting electron with a muon, the heavier cousin of the electron we met long ago in the search for Yukawa's particle. The muon is about 200 times heavier than the electron, so it orbits much closer to the proton, which makes its energy levels far more sensitive to the proton's size. Muonic hydrogen is a far sharper ruler for measuring the proton. The sharper ruler gave a smaller number. The muon measurement put the proton's radius at about 84 hundredths of a femtometer, noticeably smaller than the long accepted value from the electron measurements. The gap was tiny in absolute terms, a few hundredths of a femtometer, but it was far larger than the stated uncertainty of either measurement. Two careful methods, each trusted, now disagreed about something as basic as the size of a proton. This became the proton radius puzzle. For a while it was unsettling. A disagreement like this can mean a simple mistake somewhere, or it can mean something deeper, some new physics affecting muons and electrons differently. Physicists took both possibilities seriously, because the muon had sprung surprises before, and because an unexplained difference between muons and electrons would be a profound clue. The puzzle drew intense effort, new experiments, and careful re-examination of the old measurements, all aimed at finding why the two rulers disagreed. As the work continued, the answer came to look less like new physics, and more like the muon measurement having been right all along, with the earlier electron-based numbers carrying larger uncertainties than appreciated. Newer and more careful experiments using ordinary hydrogen and refined scattering began to agree with the smaller value. The weight of evidence settled toward a proton radius near 84 hundredths of a femtometer, the figure the muonic hydrogen had pointed to. The puzzle largely resolved, not with a revolution, but with a sharper number. The episode is a good window into how physics really works. A precise measurement disagreed with another precise measurement, and rather than wave it away, physicists treated the gap as a real problem worth years of effort. The proton radius puzzle did not overturn physics, but it tightened our knowledge of the proton and showed, again, how much careful work hides behind a single number like the size of a proton. The answer that the proton is about 84 hundredths of a femtometer across is hard won. But measuring the proton from the outside, however precisely, is not the same as calculating it from the underlying theory. The real test of quantum chromodynamics is whether you can start from its bare equations, with nothing but the quarks and gluons and their rules, and compute the proton, its mass and its size, from scratch. For decades that seemed impossible, until physicists found a way to put the universe on a grid. Quantum chromodynamics has a frustrating quality. The theory is written down completely, its equations known, and yet for the most important questions, like the mass of the proton, you cannot solve those equations with pen and paper. The trouble is the same self-interacting gluons that make the force so strange. The usual method of physics, treating a force as a series of small, clean corrections, works only when the force is weak. Inside the proton, where the strong force is strong, that method collapses. The corrections do not shrink, they explode. For years this left the theory in an odd position. Physicists were confident chromodynamics was correct, since it explained asymptotic freedom and jets and the rest. But they could not use it to compute the one number that started the whole story, the mass of the proton, from first principles. The theory said the proton's mass should emerge from the energy of the quarks and gluons, but calculating that mass in practice was beyond reach. A theory you cannot solve is a theory only half trusted. The way through came from an American physicist named Kenneth Wilson in 1974. His idea was to stop treating space and time as smooth and continuous, and instead to imagine them as a grid, a lattice of points spaced a tiny distance apart. like the intersections on a vast piece of graph paper extended into 4 dimensions. The quarks live on the points of the grid, and the gluons on the links between them. On a grid, the impossible continuous equations become a huge but finite set of calculations, the kind a computer can grind through. This approach is called lattice quantum chromodynamics, lattice QCD for short. The plan is direct. Lay down the grid, put in the quarks and gluons and the rules of the strong force, and let a powerful computer calculate what those rules produce. There is no guessing about the proton structure, no model of 3 quarks or a C bolted on by hand. You feed in only the bare theory, the quarks and gluons and their interactions, and the proton, with its mass and its properties, is supposed to come out the other end. Doing this in practice took enormous computing power and decades of refinement. The grid has to be fine enough to capture the proton structure and large enough to hold it, which means tracking the strong force field at a staggering number of points at once. It demanded some of the most powerful supercomputers ever built, running for long stretches, and clever methods to keep the calculation honest. But step by step, the lattice calculations improved, and the numbers they produced grew sharper. The payoff was one of the quiet triumphs of modern physics. Lattice QCD, fed nothing but the bare theory of quarks and gluons, computed the mass of the proton, and it came out right, matching the measured value to within a few percent. The mass that is almost entirely the trapped energy of the strong force was reproduced from first principles by a computer applying the rules of chromodynamics on a grid. The theory could now generate the proton's weight, not just describe it. This was the deepest confirmation yet that quantum chromodynamics is the true theory of the strong force. It is one thing to explain experiments after the fact. It is another to start from the bare equations and calculate, from nothing but the rules, the mass of the most common particle in the universe, and get the right answer. The weight in your hand, 99% strong force energy, can now be computed from the underlying theory. The chain from the equations to the heft is complete. Lattice QCD does more than weigh the proton. It lets physicists explore the strong force in conditions impossible to reach by hand, including what happens when matter is squeezed and heated beyond anything in the ordinary world, to the point where the proton itself can no longer hold together and melts into something the universe has not seen since its first instance. The strong force binds quarks into protons and neutrons with a grip that, under normal conditions, nothing can break. But conditions in the universe were not always normal. In the first millionth of a second after the universe began, everything was so hot and so dense that protons and neutrons could not exist at all. The quarks and gluons were not bound into separate particles. They roamed freely in a single seething soup, a state of matter called the quark-gluon plasma. For an instant, the whole universe was that plasma. As the universe expanded and cooled, that soup condensed, the quarks and gluons clumping together into the first protons and neutrons, locked away inside them ever after by confinement. Every proton in your body is a droplet that froze out of that early plasma and has stayed bound for almost the entire history of the universe. The free quarks of that first instant have been imprisoned inside protons and neutrons ever since. To see them free again, you would have to recreate the heat of the newborn universe. That is exactly what physicists set out to do. At Brookhaven National Laboratory, the same place the Omega Minus was found, a machine called the Relativistic Heavy Ion Collider was built to smash heavy atomic nuclei together at nearly the speed of light. The collisions concentrate so much energy into so small a space that, for a fleeting moment, the protons and neutrons in the nuclei melt, their quarks and gluons freed into a tiny, short-lived drop of quark-gluon plasma, a speck of the early universe recreated on Earth. The large collider near Geneva later did the same at even higher energies. What they found surprised them. The plasma had been expected to behave like a gas, a thin spray of freely flying quarks and gluons. Instead, it behaved like a liquid, and an almost perfect one, flowing with astonishingly little internal friction, more freely than any ordinary fluid. The freed quarks and gluons, even unbound, still felt the strong force enough to move together in a smooth collective flow. The early universe, it turns out, was filled with the most perfect liquid known, a fluid of pure, strong force matter. The plasma exists for only the tiniest sliver of time before it cools, and the quarks and gluons snap back into ordinary protons, neutrons, and other particles, which is what the detectors really record. Physicists study the spray of particles that comes out and work backward to reconstruct the brief moment of plasma that produced them. It is like studying a snowflake to understand the cloud it fell from. From the debris they learn the temperature, the density, and the strange liquid behaviour of matter as it was in the universe's first instant. This is the strong force pushed to its limit, and then past it. Everywhere else in this story, the strong force has been the great confiner, locking quarks away inside colourless particles, never letting one go free. In the quark-gluon plasma, for the briefest moment and only at unimaginable heat, that confinement lifts, and the quarks and gluons mingle freely as they did at the dawn of time. Studying that state is studying the strong force in a regime it almost never occupies, and the birth of matter itself. It also closes a kind of circle. We began with the proton as a finished, stable thing and worked our way inward, to the quarks, the gluons, the trapped energy, the roiling sea. Now we have run the proton backward, melted it, and glimpsed the state it froze out of. The proton is not eternal and given. It is something that condensed from a hotter, freer phase, and under enough heat it can be undone, returned to the soup it came from, the way ice can be melted back into the water it once was. Even with all of this understood, the story of the strong force is not finished. There are real questions still open, hard ones, and honesty about the universe means naming them plainly, without dressing them up, and without pretending they are smaller than they are. For all that quantum chromodynamics has explained, it leaves real questions open, and a calm look at the strong force has to name them plainly. The first is strange given everything we have seen. Confinement, the trapping of quarks, has never been proven from the bare equations of the theory. We see it in every experiment, lattice computers reproduce it, and no physicist doubts it is real. But a rigorous mathematical proof that the equations of chromodynamics force quarks to be confined does not yet exist. This open problem is considered so deep and so hard that it has been named one of the great unsolved problems in mathematics, with a large prize attached for whoever can solve it. The technical version asks whether the theory has what is called a mass gap, a proof that the strong force binds its particles with a definite minimum energy and never produces free, massless, infinitely reaching effects. Physicists are sure the answer is yes. Proving it, with full mathematical rigour, has defeated everyone who has tried. The strong force works, and we cannot yet prove from the ground up why it must. A second open question concerns the gluons themselves. Because gluons carry colour and pull on one another, the theory allows a strange possibility. Particles made of nothing but gluons, with no quarks at all, bound together purely by the strong force. These hypothetical objects are called glue balls. The theory says they should exist, and lattice calculations predict roughly what they should weigh, but finding one cleanly in an experiment has proven very hard, because a glue ball would look much like ordinary particles made of quarks, and telling them apart is delicate work still underway. There are also particles that stretch the simple rules of 3 quarks or a quark and an antiquark. For decades, every known hadron was either 3 quarks, like the proton, or a quark and an antiquark, like the pion. But the theory does not forbid larger colourless combinations, and in recent years experiments have found particles that seem to be made of 4 quarks, called tetraquarks, and 5 quarks, called pentaquarks. They are real, but whether they are tightly bound single objects or loose molecules of smaller particles, and exactly how the strong force assembles them, is still being worked out. And there is a subtle puzzle that troubles theorists more than it troubles experiments, called the strong CP problem. The equations of chromodynamics could, in principle, contain a term that would make the strong force treat matter and antimatter, or left and right, slightly differently. There is no reason in the theory for that term to be zero, yet every measurement says it is zero, or so close to zero that no one can detect any difference. Why the strong force is so perfectly even-handed when the theory allows it not to be is unexplained, and the leading proposed answer points to a new particle no one has yet found. These open edges do not undermine the theory. Quantum chromodynamics is one of the most thoroughly tested and successful theories in all of science, confirmed in countless experiments, able to compute the proton's mass from scratch. The open questions are not cracks in the foundation, but frontiers at the edge of a well-built structure, the places where our understanding runs out and the next discoveries wait. A mature science knows exactly where its knowledge stops, and chromodynamics knows. It is worth holding both truths at once, the way a patient teacher would. The strong force is understood deeply enough to explain why you weigh what you weigh, to compute the proton from bare equations, to recreate the matter of the early universe. And it is still mysterious enough that we cannot prove confinement, cannot cleanly catch a glue ball, cannot say why the force is so even-handed. Both are true. The honest wonder is in holding them together, neither overselling what we know nor hiding it. So we have followed the strong force from the weight in your hand all the way down to the open questions at the bottom of physics. It is time to climb back up, to return to where we started and answer, in the plainest words, what we have found. Pick up that object again, the coin, or the key, or the stone you started with. Feel its weight in your palm. You now know what that weight truly is. It is not the heaviness of solid stuff packed together. It is, almost entirely, the energy of the strong force, locked inside the protons and neutrons that fill the object, made into mass by the equation linking energy and mass. The heft you feel is a force you cannot see, bottled inside particles you can never open. We can now answer the question the title posed, in the simplest words. What is the strong force hiding inside every proton? It is hiding the source of mass itself. Inside the proton, 3 light quarks are bound by gluons into a churning storm of energy, and that trapped energy, not the quarks, is nearly all of the proton's weight. The strong force hides, inside every proton, the reason that matter is heavy at all. The weight of the world is the strong force made solid. Think back over the climb it took to see this. The atom turned out to be mostly empty, with a tiny dense nucleus. The nucleus should have blown itself apart and did not, held by a new force no one could name. That force was carried by particles, the pions, then traced to deeper objects, the quarks, with their impossible fractional charges. The quarks were found to be real but forever trapped, bound by a new charge called colour and by gluons that uniquely pull on one another. From that one fact, the whole strange behaviour followed, the freedom up close, the unbreakable strings, the trapped energy that is your weight. And we found the edges of our knowledge too, the thing still unproven and unseen, the confinement we cannot derive, the glue balls we cannot catch, the even-handedness we cannot explain. The picture is deep and largely complete, and it is candidly unfinished both at once. That is the real state of the strong force, and there is no need to pretend otherwise. The wonder does not need the gaps filled to be real. Step back and consider what this means for you, standing here holding a small, heavy thing. Nearly all of your own mass, the weight of your body, the substance of your bones and blood, is strong force energy bound inside the protons and neutrons that make you. You are, in the most literal sense, mostly bottled energy, mostly the trapped fury of a force confined to spaces too small to see. The solidity you feel when you press your hand to a table is real, but underneath it you are far more force than stuff. And the same is true of everything. The mountains, the oceans, the planet turning beneath you, the sun pouring out light, the distant stars, the whole visible universe, weigh what they weigh overwhelmingly because of the strong force trapped inside their protons and neutrons. The matter we can see, all of it, gets its heft from this one hidden force locked in the hearts of atoms. The strong force is not exotic and far away. It is the reason there is weight in the world at all. So the next time you lift something and feel its weight settle into your hand, you can know what you are holding. You are feeling a force at work in a place smaller than you can imagine, a storm of gluons and quarks that has been churning in every proton since the universe was a fraction of a second old. The weight is ancient, and it is everywhere, and it is the strong force quietly holding the world together and giving it mass inside every proton in your hand. That is the strong force, and that is what it has been hiding. Hold the weight a moment longer and let it mean what it now means.